So when I was thinking about what to talk about at this ESUG, I was just starting to read a lot of papers about the concept called ownership, and so I thought, oh, maybe it would be nice to give a lecture about that, so that for something outside of Smalltalk, where people can maybe discover the concepts that other languages use, with the idea of course, thinking maybe this could be interesting for Smalltalk too in some form. But then, while preparing the talk, it turned out to be quite boring for this part of the talk. And another thing is that the slides where I tried to introduce a problem got more and more and more and more. So I actually decided to kind of give a different talk. So there will be ownership, and I will explain it at the end, but it will not be the only focus of the presentation. Because I want to explain the problem that is all about, and this goes even beyond just this ownership idea, which is more like a solution for part of it. So what do I want to talk about? I want to talk about the object graph. So this is one thing that we actually do not really think about too much in Smalltalk. What is it? So at runtime, all the objects that you create in your program are of course allocated, and then they have reference to other objects. That might be an instance variable, that might be an array, that might be an ordered collection, which itself is an object that contains in Pharo an array. And so this forms a graph. Every object is a node, every reference is a directed edge, so it goes from one object to the object that it points to. And the whole object is one big graph with one root, and you can reach every object by walking over the graph. Which, of course, we know because that's what the garbage collector does. So the garbage collector actually walks over the graph to find all the reachable objects, and it then says everything that I cannot reach, nobody can reach, so we can throw it away, and so memory is, can be reallocated. But it's actually, as a graph, a bit odd, because it's very much just a runtime artifact that we do not actually care about. So if you look at it, we have, for the edges, we have two cases. So we have outgoing edges, which we know as instance variables. In that case, they are even named, so we know even the role that this edge is playing in the program, if it's well designed. We know exactly how many outgoing edges we have from an object, because that's the instance variables that we can reflectively even look at. So we can ask the object, how many instance variables do we have, or if it's an array, we can know, array size of 10. All the objects that the array points to are the outgoing edges. So it's fixed, and this looks controllable. And it's local, so we just need to look at the object to know them, and very nice, and it's reflective. We have an API to even, when we are at runtime, we can actually look at it. We have we can ask for all the instance variables, we can know how big an array is, and we can access it. So this is very nice. But then if you think about, there are incoming references too. So my object, where I know that it has 5 references outgoing, it might have other objects pointing to it. And there is no way of knowing who points to me. They're completely anonymous. The number is completely unclear, so that could be none, in which case it would be garbage collector, so that means that would be an object we would not even talk about, but it might be even a lot of incoming references, and we have no clue who they are. It's completely global, so that means it can be from anywhere in the image. There could be a reference to our object. And it's completely invisible. So if I look at the object, I have no idea of who points to me. So in the end, it's a mess. An object knows what it points to, but it has no idea who points to it. And if you want to know anything, you need to do a complete visit of the whole graph to do anything. Which you know, if you ever had the problem that you had an object that didn't get garbage collected, and who points to it, and you have pointer finders that walk over the whole image to find incoming references, for example. So it's really a mess. Another thing that is interesting is that the object graph at runtime is actually something that we do not think about at all. So it's for Smalltalk, and it's not an object in the end, the object graph. So you never use the object graph as a graph for anything. So there is no API, no reflective API that deals with the graph as a graph. So we have no, for example, no API for iteration. You would think that, if I have a graph, that should be like in a graph database. It should be possible to reason about that graph, to iterate over it. So here's a block, here's a root, this is the condition, do it, VM. I don't care. Without even sending messages, maybe. So of course we can implement a visitor, and I do not argue against implementing a visitor, because the visitor is part of your program design. But there's, but you have to do that if you want to iterate. Or you could, of course, use reflection. So you can say, but for every object, I can discover all outgoing references, so I can write a reflective visitor myself, which is possible too. But interestingly, there is none. There's no default reflective visitor in the image, which I find a bit strange. The reason for that is too that the graph actually has no metadata attached. So I cannot really use it because I don't know, for example, where to stop or what I want to follow, because there's no way to annotate nodes, there's no way to annotate edges. So it's really limited as a graph. So if you compare that to a graph database, we are missing some stuff. Another thing, so we said, but the outgoing edge case, that is nice, we know exactly the route, we know even a name for them, so it's really cool, that's nice. But the problem is that for outgoing edges, we have no idea why why we reference that object when we only look at the object now. This is different to the program code. So in the program code, it might be clear the role that the object plays. But if you only look at the graph, the role is completely unclear. So for example, and that's a bit the running example of the talk, some objects are actually private state of other objects. Which, as we will see later, I think I have a very trivial program that shows that. So imagine we have an order class with items. The items is an ordered collection. We have add item methods, and then, for example, total, so get back the number of items. It is statically in the code clear that there is no accessor for items, so this is a private object, which is cool. Yeah. But if you have looked at code like that in practice, often it's actually that, but an accessor would be nice. You add an accessor, and boom, you expose that state to anyone potentially. So you could have the case that some object somewhere has a reference to items and modifies it outside of using add item, and you have no idea. And interestingly, if you do not have an accessor, we know that it's private state statically on the code, but we do not know at runtime. So if I look at the object that the items points to, I do not know that this is private state. Just not knowable. Yeah, so this is what I just said. So at runtime, it's just the graph. Item is just protected by having no accessor. And that's all we have. So for example, one thing that people sometimes say, yes, if you want to have an accessor for the items, you just return items copy. And then people cannot mess around with it, but they can look at all the items easily. So which is one possibility. But it feels all a bit that there's something missing. And this is of course not unknown, so people were talking about that, I guess, since objects were invented. But it got a bit defined in 1992 when there was a workshop somewhere where they discussed this problem. And then there was a paper, the Geneva Convention of the Treatment of Object Aliasing. And they looked at it really from this program perspective. So they do not talk about object graphs because so normally it's really interesting. Smalltalkers tend to look at programs as dynamic entities, while most other programmers look at programs as static. So they always think about text. So this aliasing problem is formulated as that we only protect names but not aliases in languages. And of course, this led to some research, And one of them, research I will show later. What I want to show first is a bit of problems that come out of this that you already saw in real life. So if you look at serialization, we have exactly the problem that we do not know what outgoing pointers mean. So a serializer is a program that takes a root object and then it writes an object graph to disk. Could be fuel, this could be soil, or whatever. It could even be some textual format. So if you serialize in STON or something like that. So what they do, they take a root and then they follow the object graph in a defined order to write out all the objects of the graph. So it's a recursive iteration over the object graph. But if you have in your graph a pointer to something like in Pharo or Greek, like the world, the morphic world, because you need it for something, then that would mean that your serializer will follow that pointer and it will serialize your whole screen with all the windows in it. Or imagine you have, by chance, the Smalltalk global dictionary referenced in your graph. Then it would go to Smalltalk global dictionary, then it would follow all the reference to all the classes, then it would serialize all the classes, then all methods, and then in the classes, all the class variables, and it would serialize everything. So what you need to do with a serializer is you need to actually model that. So if you look at it, in soil we have, for example, right now a class-side method which is called soil transit instance, which returns the name of all the variables in the hierarchy that from your point on upwards that you do not want to serialize. And in the end, this is of course a crude way of giving meaning to an edge in the object class. Another example, if you looked at the soil talk on Tuesday, is that in soil, in soil you partition your model into many graphs, and when you load it in, the root actually will be a proxy, and this gets only swapped in when you actually use it, but the proxy stays. So that means that we model actually we give meaning to the roots that we reference by wrapping them into a proxy. That's another example of a boundary definition. Another interesting case is incoming pointers. So imagine you say, oh, I would like to serialize this, put it on disk, let the garbage collector clean up, and then when I need it again, I load it back. Yeah, but there might be other people pointing to the object in your graph, and that means the garbage collector will not clean them up. So that means if you then load back, you have partly some objects still in memory that your system uses, while the object on disk is completely disconnected from that. That is a bit problematic. What in practice people do is that they actually use serializers in contexts where they actually control incoming pointers. But that, of course, means there's no guarantee. There might be incoming pointers that destroy your thing completely. Then, of course, if you know a bit about Greek or about the history, there are image segments in Greek which actually manage incoming pointers. But how? I mean, you don't know anything about incoming pointers. What they did is they said, yes, let's use the C infrastructure to find incoming pointers. So what they do is they say that if we start from a root, part of my segment is everything that I can reach that has no incoming pointers. Which of course means many things. So one thing is that I can actually define incoming pointers as known, so I can declare them, and that means that then it actually knows that there's an incoming pointer, and it will replace that incoming pointer by a proxy, so that when you load back the image segments and can reconnect, which is kind of nice, but the problem, which I think I have on the second slide, is that if by chance someone adds a pointer to your objects, you destroy what you serialize. And that happened back when people used it in Squeak. They tried to save complete morphic worlds. There were always bugs where someone said, it doesn't work anymore, why ask? There's no reference to this object, so it gets ejected out of the image segments and boom, it doesn't work anymore. So it's very brittle. You need to manually maintain the incoming pointers that you want to have known so that it doesn't remove the objects from your thing. And another big problem, which of course with small images is not a problem, but you need a full leaf scan. So imagine you have multiple gigabyte images. but you have tiny segments, this will not scale at all. So that was a bit to explain a bit the problem. And now I want to explain one idea, what one can look at. This is not a solution for all these problems at all. So the problem that I explained is much, much bigger than this. And it's not even a solution in the sense that I will show a solution for Smalltalk. I will just try to convey the idea of this so that you see what people were thinking about to actually tackle this. So back to our example. We have the items collection. Here's the code again. Yeah. And we want to model somehow the object memory that it knows that items is part of the order. And the intuition that they used is that some objects are part of another object representation. Like we saw here, there are other examples. So nodes are part of a linked list. The internal buffer in the stream is owned by the stream. You should not hand it out. All these things, and so these references should not be handed out, so that we do not misuse them, and that we know that we have no incoming references. And so the ownership, if you look at it as the most pure model, is that in graph terms, we have an owner that dominates the objects that it owns. So domination means that every pass from the root of the graph that would go to an internal object need to go via the owner. So that's with the graph theoretic explanation. I even have a picture for that. The ideas. So this is a graph theoretical definition. So root means every object that I can reach from the root that points to this one is okay, but any object that directly points here would not be allowed because that would be a pointer to the internal state that the owner doesn't know about. So that's the theoretical most strict case that one can have. And this actually was taken as the idea for a type system that was implemented as a research idea. So it is not implemented like this in language. And the idea is that you need to, it's a bit like parameterized types, so you need to have type definitions where the classes are parameterized by ownership context. And then the type system rejects statically all programs that actually have a case where I reference an internal object that doesn't, and not the root. So our example would not compile in a language like that. So this is a OOPS appel from 1998. One needs to see that this type system is makes it a bit complex to express things because I can not reference inside of an object at all. So it's not really a practical type system, but it's more like a research prototype. But this actually then inspired other languages. So there were then research type systems that I said, reading is actually not that problematic. I care only about writing. So they said, yes, it's okay to reference inside of the ownership domain from anywhere, but if you modify with that reference, then I want to forbid that. So all programs that modify a non-owned object should be rejected. Which again is much less strict, but it still solves some problems. So especially for concurrency, that is interesting. It's about modification, and for the idea that you don't want to control that nobody modifies your object without you knowing. Yeah, but it inspired then even systems that are even less strict. And one example is Rust. So in Rust, every value has an owner. And then they actually said, if assignment is not assignment anymore, so I don't make a second reference, but an assignment by default copies the object. So then I have my own private object and do whatever I want, which of course might not be very practical for many cases. So they added another concept which is called borrowing. So I can actually temporarily get ownership over an object by using a special reference. And then there are two kinds of reference, read-only references and reference that can modify, and then the rule is that there can be only one reference that can modify. But it gets quite complex in details, and so I decided that I will not do an introduction to the Rust type system, but it is interesting. It's quite complex to work with, but the payout seems to be quite high. And similar type systems are in Swift, and maybe now getting more famous in Mojo. So Mojo is a static type system for Python that they use to be able to compile Python to statically, and by having ownership and controlling that there's only one write reference possible, they actually can do parallelization. So you don't need to lock your object anymore because you know that there's only one writer. So this is that. One important thing to note is that these are all type systems. So that means they restrict the programs that are compilable so that they can only create object graphs that have this ownership the ownership definition as you define it in your type system being valid. So that's what they do. The nice thing is, of course, that this allows you to not care at runtime, so that means you don't slow down because you need to do ownership checks for maintenance at runtime. But one needs to see the object graph still knows nothing. This is completely not a runtime entity. It's just a compile time restriction of which programs are compiled. So this means that for Smalltalk, this is of course completely not a good fit. We have no types. But if you would build a type system, it might be interesting to look into ownership types too. But if you don't have a type system, this is completely makes no sense. Then we have things like reflection. We have a debugger inspector that wants to look into everything, and you want to be able to change stuff. Then we have a live system to code changes while the objects still exist. So this all does not really fit with a static view of ownership. So what we need to think about is how can we do that dynamically? And this goes a bit now back to what I was explaining before. The object graph that we have now at runtime is completely unstructured. It has no metadata, it has nothing. And I think that we should do experiments to play with this and to ask the question, can we not make the object graph into something that is reflectively more rich and has more metadata attached to it, and then have the system at runtime react to that. And so what the direction I think is that could be interesting for Smalltalk is to look at ownership as a feature of the object graph, as a reflective model of ownership that is completely independent of a type system, and that is always there, so that if you then use reflection in your program, then it actually can take that into account. How exactly, I have no idea. So this is very, very early. Another thing is, of course, huge challenges. If you model ownership on the level of the object graph, that means you need to have space to put that information. The most naive thing is to say, one instance variable per object points to the owner, might be hidden away, so you don't see it, like we have already the forwarding pointer to the object new. You don't see it, but there's one instance variable that is hidden away, so that you can store, even in an empty object, the forwarding pointer if it will become. And we could do something like that. We could have a hidden forwarding pointer into this. But that would mean that every object would have one instance variable more. That's memory. Another thing is that the whole point of this is to reject that someone could modify my internal representation, so I need to actually check. So that means that instance variable access is not just doing the change, but it means that instance variable access will say, yes, let's check if I'm allowed to do that. Am I the owner? And then I can do a store. If not, I raise an error. Which has a huge performance implication, because instance variable access is fast, but doing a check for every instance variable access is slow. So we have no idea. There are other ideas of how to implement that. And that's, in the end, the challenge to think about of what do we want. first, I guess, a simple model is interesting to actually find out what we really want from the ownership. So, for example, we have no idea yet of how ownership is declared in your program. Yeah? So we don't, if you look at the type systems, it's part of type definition. How do we do that in our language, where we have no type definition, no idea. So we need to look at many, many things so that this makes any sense.